Okay, good afternoon. Raman Research Institute witnessed a year-long celebration with numerous academic events that culminated with a grand closing event at the turn of this calendar year. This was celebrating our 75 years, the Platinum Jubilee year. So we hosted 6 international conferences, launched a number of talk series of different flavors and purposes. So we have a colloquium level talk series called the Pancharatnam Lecture, named after one of our distinguished professors here. There's a popular public lecture series called the Vigyan Kathegalu, and also another one, the Engineering Frontier Science, which conveys the role of technology in enabling breakthrough science. Then Science and Society Talks, Anusandhanenu Samaj Vikas, and pedagogical lecture series called Vigyan Pathshala. So today I'm delighted to welcome you to the inaugural talk of a new series, the Hema Ramachandran Lectures, named after our most loved Professor Hema Ramachandran, a highly respected researcher in optics and one of the founding members of the Light and Matter theme at Raman Research Institute. Beyond fostering the LAMP group, Hema was deeply involved and worked with a missionary zeal to bring about what is now well known to everyone as the National Mission for Quantum Technology and Applications. I invite Professor Urvashi Sinha to talk about Hema and also introduce our speaker, distinguished speaker, Sujatha Ramdorai, who is absolutely the best person one could think of to launch a series meant for eminent distinguished scientists in this field. Thank you.
Thanks, Tarun, and of course, thanks to the Director's Office for inviting me to present an account of Professor Hema Ramachandran's science and accomplishments. I'm basing this on an article that was written by colleagues Andal Narayanan and Rajaram Nityananda, who have worked in close association with her, and this got published in Current Science Journal after her untimely passing. And this will be very useful for the younger people at the end, back who may not have interacted with Hema. So we give an introduction to, to the best of our abilities. So Professor Hema Ramachandran, Hema, to all of us who knew her, passed away during the early hours of 24th of November, 2020, after a long illness. The Light and Matter Physics Group, or the LAMP group, of the Raman Research Institute, of which I am a part, of course, lost a fine scientist, and as Tarun mentioned, one of its founding members. After a master's degree in physics from IIT Bombay, Hema joined the training school of the Bhava Atomic Research Center, or BARC, in Mumbai. She then worked in high-pressure physics and uncovered a novel phenomena, that is a material becoming amorphous when subjected to pressure. Her contributions and promise were recognized by an INSA Young Scientist Award. Hema then moved to Bangalore after marriage and was posted at the BARC's seismological station at Gauribidnur. This meant taking up a new area of science. RRI had a close linkage with the BARC seismology group, and which had provided support for a radio telescope facility at Gauribidnur. And Hema used an office on the RRI campus when needed. So in 1995, she was offered a faculty position by the then director, Professor Narendra Kumar, who was keen to start activity in the then emerging area of light-matter interactions. Hema took up the challenge of entering yet another field. In this venture, she had strong support from R. Srinivasan, an outstanding and versatile physicist who had just retired from the Inter-University Center at Indore, and Narendra Kumar himself. Right? So looking back, of course, to all of us, it seems like she had found her true calling at that time. Hema combined ambition and determination with personal warmth. One of the earliest experiments on imaging through a turbid medium resulted in a very well-cited paper. The optics lab, as it was then known, attracted talented and motivated students and gained recognition for light scattering related experiments. The end of 1999 brought a paradigm shift. N. Kumar laid out an ambitious path. opened up by the winners of the 1997 Nobel Prize in Physics. So that was trapping and cooling of alkali atoms. And Hema's character, thriving on challenges, N. Kumar's indomitable spirit, and the strong guiding light of Srinivasan helped a team of relative novices in the field to achieve magneto-optically trapped cold rubidium atoms in October 2001, only the second group in the country to do so. With more additions to the faculty, the research group expanded to include nonlinear optics. Later, talented younger physicists trained in cold atoms joined and started new activities. Hema continued her own journey with experiments on light scattering, cold atoms, and later on the brain-computer interface, which was yet another new area. Those close to her know the enormous satisfaction each and every new result gave her. Her talents and experience were put to use across the institute, where she was made the head of all research facilities at RRI, a position she held for nearly half a decade. The LAMP group of RRI, as it is known today, is a place not just for cold atom research, but potentially an important player in the new emerging area of quantum and quantum-inspired technologies. Hema grew into a significant enabling role in developing a community in these areas at the national level. Serving on the relevant program advisory committee of the DST meant reviewing proposals for funding in this and related areas, and often interacting with the proposers. This led later to her serving on the more coordinated quantum-enabled science and technology program of the DST. She then joined a small group playing an advisory role to the larger, younger group drafting the ambitious quantum mission, of which I am a part. The funding of this mission at that time, 8,000 crores over 5 years, announced in the budget 2020, is widely known. However, less visible is the spade work which went into producing a comprehensive proposal of this scale. So Hema's role in the process leading to the formulation of the mission was critical. This is particularly poignant considering that she attended meetings, made presentations, and prepared documents, all to tight deadlines while fighting what proved to be her final battle. Hema had a fine sense of aesthetics and carried herself with grace and dignity. She was a strong feminist without ever being obvious about it. And in recent years, even when she was besieged with illness, she maintained her endearing sense of wry humor in the face of life's absurdities. The genuine affection her students have for her is a testimony to the camaraderie she had with them. And this extended to the technical staff, many of whom I can see in the audience, who play such a vital role in experimental science. She cared for them and they looked up to her. Hema is survived by her spouse, brother, and parents. It is indeed befitting that we are now launching a new series of lectures, Hema Ramachandran Lectures in her memory, to be delivered by distinguished women in the field of science, technology, and medicine. And it now gives me great pleasure to introduce our inaugural speaker in this series, Professor Sujatha Ramdorai. Professor Ramdorai currently holds a Canada Research Chair at the Department of Mathematics, University of British Columbia in Canada. She completed her PhD in TIFR and was a professor there before her move to Canada. She served as a member of the National Knowledge Commission, 2006 to 2009, the National Innovation Council, 2009 to 14, and the Prime Minister's Scientific Advisory Council from 2008 to 2014. Her awards include the Shanti Swarup Bhatnagar Award in 2004, the ICTP Ramanujan Award in 2006, and the Krieger Nelson Prize 2020, and the Padma Shri in 2023. So today she will tell us, I assume still the same topic, on problems in number theory, challenging minds over millennia. So with that, I invite Professor Ramdorai to please come and deliver the inaugural lecture.
Thank you for the kind introduction, and it's an honor, privilege, and highly humbling to be delivering the first lecture named after somebody who, as we heard, did so much for science. And that's something that I'm surprised that the way people react about women in science. Say, oh, women can actually be so passionate about science. And if you read the lectures, the essays, Leelavati's daughters, that's something that shines through. And this is another living example of women who can achieve and also be dedicated when it means something to them, and often it does. Whatever it is, it means a lot to them. So I'm going to talk about something totally shifting gears about number theory, but in the end I hope to touch a little about quantum. I read up a little about Hema Ramachandran just a couple of days back. I was very busy and I couldn't find anything in mathematics to relate to light and optics that I could talk about. But in the end, I hope to say something quantum. It's of course definitely not the quantum that Hema was probably interested in, but it's definitely relevant to mathematics, and we'll touch upon that at the end. So I'll start with something very simple. So this is the natural numbers. These are the notation I'm going to use. Natural numbers 1, 2, 3, that's just the whole numbers. Integers, everything 0 included 0, and also the negative whole numbers. Then rational numbers, of course, those which are expressed as m upon n, where both m and n are integers. Irrational numbers are those real numbers which are not rational. These are irrational numbers which are not rational. So examples, all of us know square root of 2 is rational. And then the famous pi, which is always a trick question because people learn about pi as 22 upon 7. And they're always puzzled about why it's not rational till somebody tells them that it's only an approximate value and not the real value. And oops. And then I want to jump gears and talk about equations. All of us, we learn this very quickly, how to solve equations in one variable. And then quadratic equations where you bump up the degree from 1 to 2. And we know, we learned this again in high school, how to solve a general equation of the form ax squared plus bx plus c. We know what the roots are in terms of the coefficients. Now degree 3 equations in one variable are called cubic equations. So for example, x cubed minus 1 equals 0, x cubed minus x equals 0. These are cubic equations. And I was surprised when I was looking up a bit about the history of mathematics, I was surprised to see how old this question of solving cubic equations was. In fact, the earliest evidence, this is evidence, not maybe written evidence, but evidence in clay tablets, goes back to 2000 BC. You'll find a clay tablet in the Berlin Museum, and it's a Babylonian clay tablet. And then we know how to decipher what's written there, and if you read it, it's actually a question about how to divide a certain piece of land. And then when you try to resolve it further, then it turns out to solving a cubic equation. And Alexandria, Diophantus of Alexandria, one of the famous names in arithmetic, the Greeks were particularly interested in solving such equations, but in finding integer solutions. And again, there's an interesting story here. It might be apocryphal. The Indians also, much before the Greeks, probably discovered rational numbers. They came across rational numbers, encountered rational numbers. And at that time, the Greeks were known for number theory, BC. But the story is that when they encountered irrational numbers, that is the real numbers which are not rational numbers, they got so scared, not scared, but so worried because it was something that didn't meet their expectations of an ordered world where everything had a place and everything could be explained and so on. And so people were prohibited by letting this out. The Greeks had circles, right? They had their schools and they were supposed to be prohibited from talking about it. And there's a story, possibly apocryphal, but I like to say it, that one of them blurted it out during a picnic and he was promptly pushed into the sea. He was given a burial at sea. Whereas the Indians also encountered irrational numbers, and this was because in their Vedic sacrifices, their constructions of Vedic altars had to be very precise. And so naturally, when you want to construct something and you take unit right angle triangle, then the hypotenuse is square root of 2, which is an irrational number. But then the Indians marched on saying, oh, there are so many things we don't understand. This is one of them, so let's get on with it, you know. And then you see this difference when Greeks shifted from number theory to geometry at around this point. And here's a quatrain from Rubaiyat, Omar Khayyam. And I'm not going to read it, but I like this because the moving finger writes and having writ moves on. I like to think of that as somehow very similar to what mathematicians do. We are constantly trying to prove something, and when we don't understand, we take the next paper and write on and try to find out what was wrong with the previous formula and so on. But why do I bring Omar Khayyam into this story on cubic equations? This is because he was also an astronomer and a mathematician. And in fact, he is known for a geometric solution, for using geometry to solve equations of this form, cubic equations of this form, x cubed plus a squared x equals b. Now, later on, as people understood a little more about differentiation, integration, what it meant, and so on, people were interested in studying arc lengths, and then especially in studying arc lengths of ellipses. So they could understand perfectly, they understood the geometry of the circle. The equation is x squared plus y squared equals 1 if you take a unit circle of radius 1, and then how you use trigonometry to measure arc lengths and all that was quite, within their reach. But elliptic integrals completely floored them. And closely related to this was a study of elliptic functions. It's a special class of functions which also was studied from the 17th, 18th century onwards. Here are some of the names of the mathematicians: Euler, Legendre, Abel, Jacobi, and so on. And what we knew, cubic equations, making this jump from squares to degree 3 equations, had a good 350-year history before people finally learned how to solve it. And there's this very interesting article for those of you who are interested. It was completely settled only by the end of the 16th century. And there's this nice article, The Scandalous History of the Cubic Formula, which led to the sordid past of the cubic formula, the quest to solve cubic equations, which led to duels, betrayals, and of course modern mathematics. So this is Euler, this is Abel. But now I'm going to bump up one more. So f of x is a cubic, in the sense it's a cubic equation in one variable, but I'm going to add another variable, y squared. That's a quadratic, that's a degree 2. So now this is an equation in 2 variables, and you can plot it on the real line. We all know a circle, we know a parabola, those equations look like this, except f of x is not a cubic in those cases. But suppose I take y squared equals f of x, and this is a cubic, and I'm going to insist that f of x is actually a cubic, and it's a polynomial with coefficients in the field of rational numbers. So here's a simple example, y squared equals x cubed minus x. So the right hand side, of course, I can factor it as x into x squared minus 1. So which is x into x minus 1 into x plus 1. So it has 3 distinct roots. So that fits our requirements. And I can plot it and view it as a plane curve. That is, when I plot it, when I look at the real points, its set of real points looks something like this. But now cubic equations, now I'm going to call all these solutions. So take a cubic equation f of x with distinct roots, and then look for solutions, the plane curve y squared equals f of x, look for all the solutions. And I'm going to add one extra solution. That's important. That's a solution at infinity, which you really get by homogenizing this. You see, the right-hand side is a cubic, so it's a degree 3 equation. The left-hand side is a degree 2 equation. I want to homogenize it. I want to make every monomial of degree 3, so I'm going to introduce an artificial variable, z. So the right-hand side will become y squared. So for instance, if you look at this equation here, so this will become, if I homogenize it, it's going to become y squared z equals x cubed minus xz squared. So that's the way I'll homogenize. Then you automatically get one point, which is 0, 1, 0. And that I'm going to call the point at infinity. That's important because for elliptic curves have to have a special point. And now what is interesting about such equations? So when I take all these solutions and then add this extra point, then miraculously I can add the solutions, not in the sense of coordinate addition, not if I take 2 solutions x0, y0 and x1, y1, not just adding x0 plus x1, y0 plus y1, that's not going to give a solution. But you have to use geometry, serious geometry, to actually find that you can add 2 points and get a third solution. Take 2 solutions, there's a special way of adding them, and that gives a third solution. And for those of you who know a little bit of mathematical terminology, this means that this set of solutions actually has an abelian group structure. Just like the integers, you can add 2 of them, there's a special point, just like you have 0 in the integers. When you add anything to 0, you don't get anything new. And then when you take any number and add the negative of that number, you get this special value 0. So something like that happens even for this E of Q. I can add 2 of them and then get another point in the same set. And then there is a special point which plays the role of 0, namely this point at infinity. If I add anything to that point, I don't get anything new. And then for every point, there is its negative, such that when I add those 2 points, I get the special point at infinity. So it has the structure of a finitely generated abelian group. And this is true not just for the rational numbers, but I can look for solutions over any field. I can take a cubic over any field. It can be the reals, it can be even integers or more special fields, the complex numbers or finite extensions of the rational numbers and so on. But problems related to elliptic curves were studied in a totally different context and from around the 10th century, and we shall see that below. Okay, now this is a theorem that I wanted to say. So now, because it has the structure of a finitely generated abelian group, all you need to know that when I look at all the solutions, then I can pretend, I can forget that there's something in the background, we are solving equations, etc., and then just see that there are that many copies, some particular number of copies of the integers, the usual integers that we know, and something which is finite. And one of the most interesting problems in number theory is to understand what is this G, even in the simple case when the field is the field of rational numbers. Now this happens only for, this becomes only when F is a finite field extension of Q. In the sense, so for instance, let's pretend that it's just Q, then only then does it have such a structure. For instance, if you look at this over the complex numbers, it's definitely not going to be something like this. It's going to be a torus. For those of you who know topology, it's actually two generators and it's a torus, so it's much more, it's studied more from a topological point of view or from an algebraic geometric point of view. But for number theorists, this is something very compact, and then you're interested in understanding this invariant, and then what does this finite group look like. And there's a very deep conjecture, this is one of the millennial problems, which says that this, this is just algebra, that this algebraic invariant, conjecturally, if you believe a famous conjecture for which you will get $1 million if you prove the conjecture, you will get $1 million if you disprove the conjecture. And if you do that, then this is an analytic function. You define a power series, this is actually a power series, and you take the value of the power series at s equals to 1. This is something which is analytic. It has nothing to do with algebra, it has nothing to do with the elliptic curve, though of course the equation comes in when you want to define this elliptic, this L function, it's called the L function. And to see that these two things are related, and this was done in the early 60s by this pair of Cambridge mathematicians, Birch and Swinnerton and Dyer, who in those days sensed that something like this must be true and used a very, very basic computer to test their hypothesis. And they found that this was true for, and today we know that it's true for thousands and thousands of elliptic curves. But there's no general proof which explains why this should be true. Of course, there are advances. We now know philosophical reason for why something like this should be true, and this has also led to great advances in mathematics. But let me come back to this connection with cubic equations that I said we'll come back to. So we all know Pythagoras theorem. So take a right angle triangle, A, B and C are, A and B are the sides, C is the hypotenuse. Then we all know Pythagoras theorem, A squared plus B squared equals C squared. And then numbers, these triples, A, B and C, which satisfy this property, are called Pythagorean triples. So I'm looking for rational numbers A, B and C such that A and B are the sides of a right angle triangle. So half AB, which is the area, that's again a rational number. And then there is this identity, A squared plus B squared is again the square of a rational number. Now such triples are called Pythagorean triples. Now certainly ancient Indians, we know that from the 8th century BC in the Sulva Sutras, people have been thinking about this. Pythagoras, Baudhayana for instance knew Pythagoras theorem before Pythagoras. And there are infinitely many Pythagorean triples because you can convert this to this is like an equation of a circle. If I divide by C everywhere, then I just get A1 squared plus B1 squared equals 1, that's the unit circle. And we know that there are infinitely many points on the unit circle. So this one has infinitely many solutions. And integer, but now if we are interested, congruent number is a number, we say that there is, a number is a congruent number if you have these such triples. You are looking for triples A, B, C, which satisfy this identity, and half AB, which is the area of the right angle triangle, has to be this number M. And we can take M to be a whole number. So we are interested in what kinds of numbers, whole numbers, are actually congruent numbers. So for instance, again the Arabs are from around the 10th century, they knew that all these numbers are congruent numbers. 5, 6, 7, 13, 14, 15, and note, these are congruent numbers. Already to write down a right angle triangle whose area is 5 is not trivial. So this is the area this is a right angle triangle, whereas 6 is surprisingly easier. We all know 3, 4, 5 and the area of this right angle triangle is 6. 157 strangely is a congruent number, and this is the simplest number, rational area, right angle triangle with rational sides whose area is 157. And this required computers to come up with this. But what does this have to do with elliptic curves? And then of course you ask mathematicians, we typically ask, you can always go up to squares because everything a squared plus b squared equals squared. So if I know that a number is a congruent number, its square is also going to be a congruent number. So then what is the smallest congruent number? That's one question, and the answer is the smallest congruent number is 5. And for a long, long time, people tried to prove that 1, or for that matter, any square is not a congruent number. They suspected it, but nobody could come up with a concrete proof. And then the second question we like to ask is, how do we detect congruent numbers? And later, with the advent of computers and the play between number theory and algorithms, people started looking for an algorithm which could be implemented on a computer, wherein you fed a number and the computer would answer saying yes, congruent, no, if it is not congruent. Can we do that? These are the two questions that people will ask. And we know, if you believe this conjecture that I told you, the Birch and Swinnerton Dyer conjecture, which is a millennial problem, it still hasn't been solved. But if you believe that, then conjecturally there is a finite algorithm with finitely many steps which will give us the answer. But that's dependent on the conjecture. And then you ask, how complex can this algorithm be? And then we know the answer even for that. If n is congruent, if you take a natural number n, you want to know that it is congruent, then it involves an algebraic computation which is approximately this size. So as n grows, it's n to the power 3 by 2. So it's still implemented, the complexity is not too bad. And the proof that 1 is not a congruent number, you're asking if squares are congruent numbers, and this took a long time. And this was due to Fermat, and uses what we call in mathematics as principle of infinite descent. This is Fermat, and I'm sure all of you know the story where he said, I have proved, related to this, he could give a complete proof that 1 is not a congruent number, but related to that was looking for solutions for y squared equals f of x. Remember, that was what we started with, y squared equals f of x, where f of x is a cubic. And this problem turned out to be closely related to that. And then he suspected an answer for that, and then he wrote the famous statement on the margin saying, I have found a fantastic proof, but unfortunately this margin is too small for me to write it down. And then mathematicians spent the next 350 years. But now we know that he probably had a wrong proof, and we can guess, we can retrofit into his brain and see what are the mistakes that he could have made. And then we know that he had a wrong proof. The proof was not correct, and we also know the mistake that he probably made. But it took 100 to 150 years for people to understand what was the mistake that he made. And Fermat again was a polymath. Now there's a finer analysis of congruent numbers. So you want to analyze, so the question is this, you have a whole number n, when can I find a right angle triangle whose sides are all, let's say, rational numbers or even integers, and we want to, sorry, but I don't know how to put this phone off. And how do we use the fundamental theorem of arithmetic? So the fundamental theorem of arithmetic is the statement that every number can be written as a product of prime numbers. Again, that goes back to Euclid before Christ. We know that it's at least 3,000 years old, but it's probably much older. We have enough evidence to show that other civilizations knew about it, except they didn't express it in that way. And take the case, so now we want to understand what kind of numbers can be congruent. And so there is this number, whole number. So then you break up the question into take a prime number, when is a prime number congruent? And then take product of two primes. We know that every number can be written as a product of primes. So then you come from that perspective. Take a prime number, what are the primes which are congruent? And then what are the primes, if you take a product of two primes, when can you say that they are congruent? And right now we are just at the border of, what can I say when a number n is a product of three primes? But going back to this table which I showed you, which came from the 10th century, if you look at this table, 5, 6, 7, 13, 14, 15, what something, you notice that there's a pattern. You're just going modulo 8. You're adding 8 to the first 3 numbers, right? And already then, and you see, it's really phenomenal how they must have come up. There's a long list. The Arabs have a very long list. And we already saw that writing, for 157, we saw how horrible it was to write down that associated right angle triangle. So how did the Arabs come up with that? They knew the connection between this problem and elliptic curves. And that was the only way they could have come up with this. And then that leads to a conjecture that, take any number, any whole number, and suppose it leaves a remainder of 5 or 6 or 7 modulo 8. So divide that number by 8, and if it leaves a remainder of 5, 6 or 7, then it has to be a congruent number. So that's a conjecture. Today we are within grasp of that, and we have proved, I would say, around 70 to 75% of that conjecture. But that led to 350 years of understanding what Fermat had in his mind. Yeah? Okay, so now because we are talking about primes and we are talking about how to analyze numbers which are products of primes and find out if they are congruent, we know that there are infinitely many primes. This is something we have known for a long time. Though I am still surprised this proof is not taught in high schools in India. And there's a great discussion right now whether what should we do, how much of proofs should be taught in high school, should we just let them experiment, etc., etc. But this is one of the simple proofs if taught correctly, if taught the right way. Now, we know that there are infinitely many primes. We knew at least for 4 millennia we have known this. But then what can you ask? You can ask for primality testing. If you are given a small number, small in the sense up to maybe even up to 6 digits, you can do by hand. You can work out whether a number is a prime or not. You have to know how to take square roots. But once you take square roots, then you can apply what's called the sieve. You sieve out all the numbers which are not primes, and then what remains, they are probably primes, and then you can run a finer check on that. So we know how to test for primes when the numbers are small. But we want to ask a similar question. There are infinitely many primes. So as the number becomes larger and larger, let's say a billion digits or tens of billions of digits, then how are we ever going to find out if the number is a prime number? So that's called primality testing. And that again took a long, long time to come up with an algorithm and today we have an algorithm. And it's interesting because Manindra Agarwal, one of the Indian mathematicians, was famous for that. He, along with his undergraduate research students, the question that people had was, if you are given a number, is there an algorithm which is implementable with not too much complexity? What do we mean by that? As the number gets larger, the number of steps in the algorithm shouldn't grow exponentially. At most, polynomial growth is allowed. Then you can implement it on a computer, and then within reasonable amounts of time, with a reasonable computer, you can get an yes or no answer. That took a long time. Even with advancement of computers, it couldn't be answered unless you used corresponding advances in pure mathematical research. So then the two of them were happily married, and then today you have an algorithm which will tell you in polynomial time whether a given number is prime or not. But now take the other opposite problem to this. So primes are the basic building blocks. So given any number, you know that it is made up of prime factors. You can break it into prime factors, and prime factors cannot be broken into smaller numbers. But now if I give you a big number, and I know, suppose we apply primality testing and we know that it's not a prime number, then I know that it has to have prime factors. How do I find a prime factor? That problem is still widely open. We don't have an algorithm for that. As the number grows larger, there is no algorithm which will tell us how to factor or how to find a prime factor for that number. And combining this simple fact that this is a two-way operation, multiplication and factorization, these are two-way operations, right? This is the opposite of one another. And combining the fact that multiplication is easy, even your handheld mobile phone, the most simple mobile phone can multiply huge numbers in a fraction of a second. But if you give your number a big, even the most powerful computer, if you give it a big number, it cannot find a prime factor. Exploiting this simple fact that there's a two-way function opposite to one another. One way is easy, you can even tell the whole world. but the other way, you have no clue on how to do it. This simple principle is exploited to make all our so-called internet banking, cryptography, everything secure. And mathematics abounds in such two-way operations, where one-way operation is easy. There is an inverse operation which is substantially harder and requires very deep concepts from mathematics. And then you convert this into an algorithm and convert that into a crypto system. And elliptic curves, which we spoke about just a while ago, are ideally suited for this. For instance, the addition operation that I mentioned on the elliptic curves. That's again a two-way operation, because addition we know has an inverse, namely subtraction. So even this addition operation on elliptic curves has a corresponding inverse operation. Namely, you take any number, it has an inverse, where I get this special number which I called the point at infinity. But how do you do it? What is the operation for addition? And then how do I convert that into a crypto system? That after using large prime numbers, in fact, there was a time when number theorists would patent the next largest prime that they found out. And as we speak, there is a whole, there's an internet search which is called GIMS, Greatest Internet Mersenne Prime Search. There are groups of people around the world trying to find the next largest prime number. Even though there are infinitely many prime numbers, we also know that prime numbers get sparser as you go further and further. So already if you look from 1 to 100, 1 to 20, you can find so many prime numbers. And 1 to 100, it's not proportional. It's not 1 to 10 if you have x, then from 1 to 100, it doesn't automatically become 10x. So there's no known formula, but mathematicians know what is the number of primes. If you take any real number, x, then what are the number of primes which are less than or equal to x? Asymptotic formula for the number of primes less than or equal to x. This was known, and people like Euler, Riemann, and our own Ramanujan did it with just pen and paper in their head. And these operations went on later into devising crypto systems which were more and more secure. And once the computers got powerful, it became very clear that you're using prime numbers, and you're using this fact that if you're given a big number, you cannot find a prime factor. But as computers became more powerful, it was clear to the mathematicians that you could eventually find, if you had a mathematician who knew what was the mathematics that went into the crypto system, then you can break it. And so they were no more as secure. And then came elliptic curve cryptography, what is called elliptic curve cryptography, where operations on elliptic curves, similar to this multiplication and factorization, inverse operations which you perform using elliptic curves, coming from solving these equations y squared equals f of x, and exploiting the fact that there is an additional structure on that, those were used to build stronger crypto systems. And it's called ECC, elliptic curve cryptography. And later it was pushed one step further towards what's called hyperelliptic cryptography. And that's somewhere where we stand today. Still difficult because you need to know deep mathematics. And the computers, you can use prime numbers along with elliptic curves, and you can use large prime numbers, which makes it difficult even for the strongest computers to break the crypto system. So that's where we stand today. Now, since we're talking about primes, we can ask lots of other questions about prime numbers. So one, as I mentioned, as we go farther out there, when we are looking for larger and larger primes, we know that there are fewer and fewer. The gaps between them become larger. But still, there are infinitely many of them. So I should find the next prime number. And then what do mathematicians do? So the typical way we think is, okay, maybe we are searching in too large an area, because you are searching amongst all numbers, you are looking for the next prime number. And there are these special classes of primes which are called Mersenne primes. I won't define them. And we know that if you know a prime which is a Mersenne prime, so let's say M is a Mersenne prime, then you look for numbers which are of the form 2 to the power m minus 1. And there's a good chance that if you get lucky, that can be a prime number. So you first search among the smaller classes like this. So among the prime numbers, you look for numbers which are of the form 2 to the power p minus 1, where P is a large prime number, and then you run your primality test to see if this number is a prime number. Then you have dramatically increased the size. From P, you have gone to 2 to the power P minus 1. And again, we have enough tools and ammunition to do this with the existing computers. So that's one of the ways in which, but again, current computing power is not good enough for a single computer or a single person to check this. So there are groups which divide this amongst themselves and do that. And anybody typically who discovers the next biggest prime number gets a prize, non-trivial amount of dollars, and soon a company will come and patent it and so on. Now, so there are other important conjectures which are really not still open, and again, very simple to state. And this is one of the hallmarks of mathematics. When I was in Tata Institute, I always used to be surprised. The physicists used to make fun of us because we were going into the library and looking at papers which were, 35 years old, desperately looking for somebody who would translate a Russian paper from the 30s into English, or a German paper from last century into English, and so on. Because for them, anything which was more than 2 weeks old was not worth looking at. So they would always make fun of us. But that's the nature of mathematics. You never know. I mean, just think of this problem. After all, humankind has thought about prime numbers for thousands of years, not ever thinking that one day it's going to play a crucial role in cryptography, and internet banking would be impossible without prime numbers. So there is this other conjecture. So we are going to call twin primes or two quote-unquote consecutive primes. Of course, two consecutive numbers can never be prime numbers, because if one is a prime number, then the next number has to be an even number, and that's not going to be a prime number. So by consecutive primes, we mean numbers of the form n and n plus 2. So 3 and 5, those are prime numbers. 5 and 7, so this is again a twin prime. 11 and 13, 17, 19. So numbers like that are 29, 31. These are all twin primes. And mathematicians have long conjectured that just as there are infinitely many primes, there should be infinitely many twin primes. Now this is such a simple statement to state, right? I mean, anybody who understands prime numbers, you can state this, and then you tell them there are infinitely many prime numbers. Then the question is, are there infinitely many twin prime numbers? Nobody knows. It's believed. There's a lot of evidence to support that, but nobody has any reason or any proof for why there should be infinitely many prime numbers. And again, this powers much of modern research, or they find that something else done in some other corner of number theory or in other corner of geometry of real numbers suddenly has some connection with this twin primes. And then people get excited, and there are important advances have been made. But this problem in this full generality still remains open. And here is something that's even simpler. So you look at this conjecture which was made around, so it's relatively very young in human thought if you go back to prime numbers and Pythagorean triples and so on. So this was around 1742. It's called Goldbach conjecture, which says that take any even integer greater than 2. So 4, 6, 8, all those even integers. They have to be a sum of two prime numbers. And again, we are far from knowing the answer for this. But then how do mathematicians typically answer, or rather, how do we think about these questions? Then one way to do this is to say, okay, how far can I go to show that how far an even number, among the even numbers, how far can I go to show that any even number less than or equal to that number has to be a sum of two prime numbers, right? So by bare hands, people could do it for quite decent, I think up to tens of thousands they could show, long before computers came into play and so on. Now later with computer methods, they could show more and more, could go to very large numbers and show that up to that number, every even number is a sum of two primes. But then, as the numbers get larger, you have to embed more and more techniques. You have to show that it's a sum of two primes. So you have to, first you're going to exhibit it as a sum of two numbers, and then you have to prove that those two numbers are prime numbers. How do you do that? Okay, we know primality testing. But then, it's no more, even with advances in computers and with advances in pure number theory, it's still not doable for very large numbers. You still don't know how to write a large even number as a sum of two primes, even though abstractly you know that it should be, because we have proven that all numbers less than or equal to this big even number should be a sum of two primes. But to actually exhibit two prime numbers so that this huge number is a sum of those two primes, that requires more techniques and so on. And these typically are examples of, one day when this conjecture is solved or when this is implementable on a computer, maybe we'll get a more secure crypto system. And this requires close, you need computational mathematics, you need abstract mathematics. I cannot stress enough the role that pure mathematics plays into this. Because often even the most powerful computers, for instance, when I spoke about that elliptic curve which we started with, and then I said we are interested in understanding the rank, right? So let me go back to that slide that was right at the beginning. We were understanding y squared equals f of x. Yeah, where we were understanding, we were interested in finding the solutions of this. And then I said that this is actually a group structure. So you have this invariant, the number of copies of integers that are there among the solutions. So we are interested in finding this. And then you say, all right, this finite group, I have this finite group, and then I have this field, even take Q for instance. And then I want to find solutions here for special cases when we have curves of this form, y squared equals x cubed minus n squared x. So that is x into x minus n into x plus n. So that satisfies our criteria. So even for that, when I take the simple case when n is equal to p, where p is a prime number, and I put in a large prime there, then it becomes substantially difficult to find that g there. And abstractly by pure mathematics, or you can predict what g should be. But to get a computer to actually check it, even for primes which are relatively small, let's say 17, 11, the most powerful computer still cannot do it. So this field, again, elliptic curves, has this abundant number of operations which are two-way operations, but where there's very deep theory underlying it. And then it, discussing with the right kind of computer scientists and computational number theorists, hopefully there can be more secure crypto systems emerging out of this. All right, so I think, the basic goal was to sort of highlight how questions are simple, but answers are very deep. We still don't know the answers, but mathematicians believe what the answer should be. And that's supported by numerical evidence. But mathematicians are never happy with numerical evidence. We always look for a complete proof. Not just that, but for instance, for the four-color graph problem, right? Given any map, take the map, then how do you use just four colors to color the world map, let's say, such that no two adjacent countries are colored in the same color? We know that this is possible, but a large chunk of the proof uses computers. Everybody agrees on the proof. It's correct and so on and so forth. It's passed the litmus test. But mathematicians are not happy with the proof. They would like a proof without using computers. Now that's growing, increasingly getting more and more difficult these days. Especially the attraction, the lure of powerful computers encourages you to test your hypothesis. And then as you test your hypothesis, you discover how quickly you can perform calculations, and then test your hypothesis. And then when you test your hypothesis, then you see, the data that comes out. And then that gets you wondering about, my God, this data is telling me so much more. That so much more interesting phenomenon is happening. And just as there is this divide between mathematics and physics, somehow, many of the problems in physics got great impetus from pure mathematics, and the physicists, at least when I was in TIFR, and Sumati can vouch for this, the theoretical physicists would come to mathematicians and say, hey, look, all this is happening. Is there a mathematical reason why this is happening? Can you give us a reason? And in fact, all of string theory thrived because of such inputs which came from mathematics. people had done this abstract mathematics 200 years before, not ever thinking that one day it would have some connection to string theory. But today, the reverse is happening also. You know, physicists come to mathematicians, but then mathematicians look at the data that physicists have or the theory that the physicists are building and then ask, oh, is there a coherent mathematical theory that I can build which explains this phenomenon? So there's this very useful exchange for which we need people like Hema Ramachandran and the students to get passionate about that, which brings me to the last slide, which is about the timelessness of the mathematical ideas and concepts. Again, going back to what the physicist said, you know, anything that's in the archive which is more than 2 weeks old is not worth working upon, you know. Whereas for us mathematicians, going back and looking at whatever made Fermat think up of this, how could he have been wrong? Was he correct? And if he was correct, why did I not see the solution? You know, that's the way mathematicians think, which is quite different. And mathematics has a much longer shelf life, and we don't really worry about, you know, is it one day going to be useful? And just the fact that there are two different areas within mathematics, for instance, you know, this elliptic curves example, where you had a purely geometric question, right angle triangle, areas whose lengths are rational numbers, and then what are the, you know, numbers which are congruent. That has deep connections with the theory of elliptic curves. I didn't go into that in detail, but it just amounts to solving equations of the form y squared equals x cubed minus n squared x. If you want to find out whether n is a congruent number, then it is very closely related to finding solutions of y squared of this elliptic curve. Y squared equals x cubed minus n squared x. So for mathematicians, just finding these inter-subject connections is actually thrilling enough. And then it gets beyond thrilling even if we don't understand that when it spills over into other areas such as physics, theoretical physics, and so on. So elliptic curves, again, these are the simplest. I want to end with two other statements. So one is this one, the conjectures. We also touched upon various mathematical conjectures which are very simple to state. Goldbach conjecture, the twin prime conjecture, and they show that the nature of deep problems in mathematics, the very nature of the subject is such that they are simple to state, but require sophisticated methods which often take centuries to build. But once they are built and you see that whole picture, that's the most thrilling moment for a mathematician. And even today when, you know, I give lectures, master's level lectures, and teach students how to solve cubic equations. After all, we know nobody needs to be taught how to solve linear equations. They are simple. Quadratic, we know the formula. You know the solutions purely in terms of the coefficients, minus b plus or minus square root of b squared minus 4ac upon 2a. So you know the roots, and the roots are in the terms of these coefficients. Now you can ask the same question for cubic equations, quartic equations, equations of degree 4 and so on. Namely, if I am given an equation, can I find the roots using the coefficients? I'm allowed to operate, multiply, take square roots, take third roots, take fourth roots and so on. Can I find the roots by just manipulating the coefficients? And it took 300 to 400 years to find out, yes, you can do it for cubic equations in one variable. You can do it for quartic equations, but that builds upon what you know for cubic equations. Then mathematicians got optimistic at one point. Euler, Abel, and all of them got optimistic, and they said, oh, maybe we can do it for all equations, equations of any degree. If we know the coefficients, maybe we can write down all the roots of that polynomial in terms of those coefficients. But then came along Abel, and he showed that this stops at 4. You cannot do it for greater than or equal to 5. There might be equations where you can find the roots using the coefficients. But given a general 5th degree equation, you cannot find all its roots just using the coefficients. And that is theory. And to show that, he used beautiful ideas from, you know, plain hands, a little bit of geometry, and what today we call as group theory. And all these perfectly fit together. And then for those of you who know the name Galois, again, for those of you who don't, you should go and read about him, how he combined solving equations with this beautiful emerging subject and presented a clear picture of why this stops at 4 and doesn't go beyond 4. So mathematicians are often looking for the larger picture. Even though we understand only very small parts, we are still looking for the other pieces of the jigsaw puzzle to fit them together and get a complete picture. And I'll stop with one other statement about elliptic curves, which we started with. For those of you who know the Riemann zeta function, this is just the function 1 over summation, take this is an infinite sum, 1 over n to the power s, where n varies. S is a complex variable, n varies from 1 to, so it's 1 plus 1 over 2 to the power s plus 1 over 3 to the power s and so on. So treat s as a complex variable. Now the values, now this looks like an infinite series. We know where it converges, which part of the complex plane it converges. And then it also has an infinite product expression. It's an infinite series, but you can also write it as an infinite product using the prime numbers, which is again miraculous. And it's an open problem, we don't understand. There's this famous conjecture on what are the zeros. So you now treat this as a function of a complex variable, and there is a conjecture about where the zeros of this function should lie. And then a lot of theory will go about how close, can I find a zero? Okay, you're predicting that the zero is on this line. Let me show that there are no zeros epsilon away from this line, or epsilon away from that line. But we still are nowhere near showing that all the zeros lie only on that line. But that values of the Riemann zeta function are of deep interest to physicists today. And not just physicists, I was recently reading that cosmologists are interested in that. Because there are some constants that come up in theoretical cosmology, which are, for some strange reason, values of the Riemann zeta function. And so people are suddenly interested in number theory. Physicists are again interested in number theory. And again, string theorists are also interested in what are called Calabi-Yau manifolds. And the elliptic curves that I spoke about are the simplest Calabi-Yau manifolds. They are the manifolds, Calabi-Yau manifolds of dimension 1. And whatever we built for elliptic curves over the last 500 years, physicists are trying to see how much of that carries over for Calabi-Yau manifolds or for higher order elliptic curves or abelian varieties of bigger dimension. So I think this, for me, proves the timelessness of mathematics as a subject, the techniques that are used in mathematics, as well as the power of abstraction. And finally, I had the opportunity to use the word quantum. As we enter the quantum era, we know very soon that quantum computers might be a reality, and then every existing secure crypto system is no more secure. And so mathematicians are sort of abstractly investigating what are the right kinds of objects so that we can devise quantum crypto systems. And that again, not very surprisingly, uses very high order mathematics, abstract mathematics. Of course, it also needs a lot of crosstalk between mathematicians and computer scientists, theoretical computer scientists, which in my opinion is not happening as much as it happened between the mathematicians and the theoretical physicists. But it has to be, and it has to happen, and perhaps Hema's project in the quantum mission, which I hope the finance minister, by the way, I hope she released the money. And if that happens, and then youngsters work on it, it's absolutely necessary. We cannot be behind, because as we know, wars are going to be fought on a different arena. And quantum security is imperative once quantum computers become a reality. And we should pull up our socks, and I'm absolutely sure that pure mathematics will have a great role to play in this. So thank you for your attention.
Thank you very much. It was a mesmerizing talk. And I think I followed 24 slides, all 24.
Good, fantastic.
So thank you very much. It was thrilling. So open to questions from the audience. This is a huge mic. Yeah. They're still mesmerized. Yeah, Sadiq, please.
Hi. Just wondering, what is the status of proof by computation these days in pure maths? Because increasingly, mathematics is also moving towards a lot of computation. And how does it affect fields like number theory and so on?
No, it's very, very beautiful. There's a very nice interplay, because like I said, we can do computations now much faster than what we could do by hand, especially for elliptic curves and so on. So for instance, if you believe the Bird-Swinnerton-Dyer conjecture, we know we have to believe it because it's true for a large class of curves. And one way that people actually check this is prime by prime. And computers can do it in a jiffy like this. And then they produce this enormous amount of data. And then you look at that and you actually see patterns. And then you go back to this table and ask, why are these patterns happening? And you uncover newer results in number theory. So it's very effective. So the way I work, I'm very bad at technology. I know absolutely no programming, no coding, and so on. But sadly, what happens is all the great mathematicians who know a bit of theory, especially youngsters, and there were a bunch of them around the mid-80s onwards. But then Google's followed all of them. They created all these wonderful programs, classified all the elliptic curves. You could do your computations if you had a certain hypothesis. One other thing that mathematicians like to do, especially after the advent of computers, was you prove a certain result under certain hypothesis. But what makes you think that the hypothesis actually happens in real life? You're proving a theorem under condition 1, condition 2, condition 3, condition 4, let's say. How do we know that conditions 1, 2, 3, and 4 really occur in real life? That requires testing your hypothesis, and often you cannot do that by hand. And that's where computers come in tremendously useful. And people prepare large tables of computations, and then you search them and you say, okay, it's not an empty hypothesis. Because there have been cases of the opposite, where mathematicians have proved an abstract result, and then somebody else comes upon later and say none of those hypotheses can hold. So it's an empty result, right? Because you're proving something under certain hypothesis, but then you know that that hypothesis is never going to be true. So such pitfalls are definitely avoided. And like I said, there are these beautiful tables. It's called LMFDB, large forms, modular forms database, large elliptic curve and modular forms database, which is an amazing resource, and it's also somehow very cooperative. So if I need to do computations for some area that I'm working in, I work and I create a notebook within that software and post all my results, so that the future people who are interested in that part don't have to do those computations again. And then if somebody else is working and looking for examples, they just have to skim through this and then come up with examples. So it's very useful, very productive, but like I said, I think for a very long time, there was also suspicion, because theoretical mathematicians, as I said, like to have a proof which is purely theoretical. Because classification of groups, there are what are called finite simple groups. What are the possible finite simple groups? There was a long list which was mathematicians claimed it was exhaustive, and they said these are all the finite simple groups. And later on, people came and made additions. They said, oh, you have left this out. Oh, you have left this out. So we still don't know if that list is complete. But never mind, at that time when they achieved it, it was a great feat, and they got the Fields Medal and so on. So for a long time, there was suspicion in mathematics departments. If they had to choose between a theoretical mathematician and a person who was a computational mathematician, would go for the theoretical mathematician. But that's changing now. And most universities are also introducing courses in computational mathematics. And we need people with such skills in the future. If you ask a theoretical mathematician to devise a crypto system, the theoretical mathematician is not going to be able to do that. He'll say, I can tell you these are the steps, I can make you understand those steps, but for you to do computations, you do the programming. I don't know how to do that. So there's more of an active exchange now. But still, there should be much more.
Okay, I had a question which is so, there was a time when cosmologists were very interested in something called compact hyperbolic spaces, because we believed that the universe is one of them. And so at that time, in the postdoctoral time, we worked on it. So there was this beautiful, of course, it's classified, but there was also algorithmically, you could find all the volumes. What really struck me was that it's quantized. Like, there are certain numbers. Now, of course, I have not followed much about it, but it struck me as an interesting problem. Why those numbers? Is there an easy answer? Is it obvious, or is it, how do you find what is an exciting problem in maths? I mean, I was wondering, why don't mathematicians worry about what causes this
like I
discreteness?
said, it's all these connections. You do it just because it just engulfs you. You are working in your own small corner and a problem engulfs you and you are working on it. And then suddenly somebody else comes along, or you sit in a lecture and say, oh, this is exactly what I was looking for, or this possibly has connections to what I'm doing. And your example is one of the interesting ones, because I know that hyperbolic three manifolds,
Yeah.
which abstract mathematicians were trying to classify using what's called homology groups of those and so on. And today we know that there are lots of connections between that, between number theory.
Oh, so it is.
Exactly.
Okay.
And the one big name right now who's doing enormous, I mean, I wish I were not even 30, 50 years younger so that I could probably learn that in high school and so on. So this is Peter Scholz, a person who got the Fields Medal a few years back. Absolutely remarkable mathematician. And in his own language, in his own way, he has unified algebra, geometry, and number theory. Shown that what you see in algebra, what you see in number theory, what you see in algebraic geometry or some other exotic field like representation theory, they all have one common underlying theme. And this is the way they are connected. You know, but even for us mathematicians, but it's so deep. Like we'll have to spend, you know, typically all of us have spent just digging ourselves deep into one hole. That for us to emerge out of that and see that link is going to take time. So it requires training the next generation to think along those lines.
Thanks.
So Sanjeev, Sam, then Onindo.
Yeah. So, okay, I have two questions, maybe one in math and one is more sociological. But so you said this prime numbers, it becomes sparse and sparser and sparser. Right. Like, do you know in the sense that, I mean, like from evidence, not maybe proof, like how does the density goes down or the separation goes up?
No,
like,
there are lots of results known on that. So these are called gaps between primes.
Yeah, exactly.
Now what is interesting is very long time ago, Dirichley, almost at least 200 years back, maybe at least 150 years back, he proved, we all learn about arithmetic progression in school, right? So take 2, 2 plus 3, 5, 5 plus 3, 8, 8 plus 3, 11, that's an arithmetic progression. So he showed long ago that if you take any number and this common difference, the number that you're adding, if those two numbers are relatively prime, then you generate that arithmetic progression. You can find infinitely many primes within that. So from all numbers, you're looking at a much smaller set. But even there you're finding infinitely many primes. And this is true for any two relatively prime numbers. So there are lots and lots of prime numbers out there. But they do get sparse in a very precise sense as you go larger.
Yeah,
you can say what are the gaps.
Yes.
But even among the gaps, what is remarkable is if you are given a gap of a certain size, okay, let's say you are given a large integer k, and then you are given another number n, where n can be, let's say, 5, 3, and so on. So you can find 5 prime numbers in arithmetic progression with this common difference. So such fine results are known. But there's no general result which says when are you going to find the next biggest prime number.
No, like on the average, for example, if you look at the density of primes, I mean, how does it go down as a function of k?
Oh yeah, people know a lot of quantitative results on that.
Okay.
Okay.
So those
but
things
again, it's not, I cannot even make a statement without sounding foolish on that because it's so specialized, and it's again one of those areas which is very beautiful. It started out as abstract number theory, counting, qualitative and all that, but which has connections to other areas, functional analysis and so on.
Okay.
So Tao, there's this person, Terence Tao, who writes this amazing blog, which is understandable by almost anybody who wants to understand a little bit of higher mathematics, written in very simple language and so on and so forth. And he blogs regularly. Terence Tao, that's his name, he's one of the Fields medalists. So he was the one who discovered this pattern among the primes and so on. So if you read it, you'll find a lot of relevant answers to your question.
So, yes. So you said that these mathematicians and computer scientists, they don't talk to each other that much. Like for my physicists, they both look like mathematicians, right? And physicists talk to both sides. So what is the reason that like mathematicians and computer scientists, what is the reason for this communication gap between
it's changing now because the computer scientists, especially with data science, they're discovering that everything that the mathematicians did, 100 years before, absolutely what at that time even mathematicians called abstract nonsense. Because they built this whole theory just using arrows and dots. but which was actually built as a language to explain various other phenomena occurring in topology and in higher algebra. So that's called what, if people know theoretical computer science, it's called categories, category theory. Today, the data science people are finding that that is really one of the things that they are looking for to understand the data sets and how to understand data sets and so on. But unfortunately, it's growing in the wrong direction, according to me. I mean, I might be biased, I certainly am biased, but it's all being done because you want to understand big data, data manipulation, and of course data is the new oil is the punchline. So it's being done with that commercial angle in mind, rather than trying to understand a deeper relationship between theoretical computer science, the syntactical connections between mathematics and theoretical computer science.
Yeah, you mentioned that the Babylonian tablet poses a cubic equation to be solved, no? Do you know, is it known whether they could solve that problem?
I think they knew parts of it, okay, because, you know, if you, I don't know the full, this is just one example, but if you go and, you know, there are others where they actually complete it and say, this was the problem and happily it was settled to the satisfaction of all the parties concerned and so on. So they must have solved some problems.
Yeah, I have a couple of questions. So could you comment on the Langlands program, and also the second part, which might seem like a planted question, is you listed a lot of unsolved problems in number theory. So in your lifetime, would you be happy to see one of them solved? Which one would that be?
Okay, for the second one, I'm going to make it very personal and biased. It's a problem related to elliptic curves that I have been working on only for 20 years, but I would like to see that solved in my, I have a couple of conjectures and, you know, and people have made some progress, but I would like to see those conjectures, again related to elliptic curves which are, but of course all of us would like to see, and personally for me, I would like to see the BSD, the Birch and Swinnerton Dyer conjecture. The Langlands program, again, that's one of the beautiful things about Scholz's work, you know. You know, he has said, it's a meta-Langlands program. In the sense, you know, Langlands program is, after all, what are we interested in? We don't know how to solve an arbitrary equation over the rational numbers, right? That's all Langlands program is about. It's trying to understand the Galois group of Q or of number fields. And then in order to do that, we have done so much in the last 200 years. Class field theory, representation theory, etc., etc. And then Scholz comes along and then draws this beautiful wand, waves this beautiful wand and says there's something algebraic in all of this, and I'm going to flesh out the algebra. So it remains to see what impact that has on Langlands program. It already has a lot of impact. Many people who are doing Langlands program, where only a few people understood it, it's expanded beyond its frontiers. So it's very exciting.
Shantan and then Sumati.
So I have a question regarding this this vulnerability of this, let's say that classical cryptography, like using quantum computation. But I was thinking that even for like, given let's say some bank password or something, given that this number is finite and you can go, like some program can go like square root away, like even classical computer, they shouldn't take much time to be broken, right? Is there
no, it depends, of course, on how, you see, there are layers and layers of security you can build. I can use a password, but then I can use a very complex algorithm to convert this password into something super complicated.
Mm-hmm. I see.
Right? And then you need to know mathematics to come back the other way. So there are lots and lots.
So there are different layers.
There you can add these layers, and each time you work on layering it in such a way that there are two-way operations, such that one way is easy, even if you tell out the secret, doesn't matter. But the reverse way, nobody can figure it out unless you're a genius and you have the most powerful computer. That's the basis on which all cryptography operates right now.
Thanks.
Thanks for a really nice talk. But I was just going to make a comment also, because you talked about the nature of proof and the fact that, you know, computational evidence versus sort of analytic evidence. And this is, as a theoretical physicist, this is of course something that we still hold the mathematics definition of what is proof, what constitutes proof. And we still would say that computational work gives us evidence but is not a proof, because we use the language of mathematics very strictly,
Yeah.
as strictly as we can possibly in presenting proofs in theoretical physics, for example. So it's very interesting. It was very interesting to see that for us also, complexity of problems increases, right? I mean, it's no longer the simple sets of questions. You're talking about much more complex systems, typically. And looking for analytic answers becomes sort of this thing that you're looking for, but very often computational work gives you hints as to what might
Correct.
be the analytic. So it's actually very interesting, I think, even philosophically, or from a point at the meta level of what constitutes proof in theoretical physics. And since maths is our standard, and if the standards in maths, or I don't even call it standards, but the nature of proof in mathematics is changing, I think that's very interesting for physicists to learn about it. So.
Yeah, exactly. And, I mean, mathematicians, if you go by the proofs, how do they, it's largely by intuition. You cannot explain, you feel this path should be right, and then you build on a certain degree of intuition. And I always used to think, of course, I never used to speak deeply with theoretical physicists, but all my TIFR lunch conversations that I can remember of, I always, looking back, I think of that as physicists somehow converting that intuition to action. Maybe through experimental evidence or through their own building of theory and so on. Whereas the way mathematicians convert that intuition is just the hard, simple way, try to write a proof, see where it breaks down, and then say, okay, maybe my intuition is wrong, I need to mute it. But we never say our intuition is wrong. We still, for a very long time, try to go and build on that intuition, till somebody can come and prove a counterexample. Then we shift and say, okay, how is that counterexample, or why is that counterexample not matching my intuition? Let me find that out.
Hello, nice lecture, very
Thank
wonderful lecture. So the number of primes, you said that there is a formula for number of primes below some number, right? So is that exact formula?
It's asymptotic. It gives you how many primes you can expect as you go. Take x to be large and large. Then it says the number of primes less than, how does it grow? That's what it says.
How does it grow? But does it give exact number?
No, it's just an asymptotic formula. It tells you cannot hope to find some more number of primes than this.
Okay.
Yeah.
So this is Gauss, right?
Yeah. Prime number theorem.
And
That's what it says.
other question, I have another question. For proving the Goldbach conjecture, has anybody tried method of induction? No.
How can you're not going to, because we don't know, as I said, if you're looking for twin primes, just forget twin primes. You can't use induction even to say what the next prime is going to be.
No, suppose, no, Goldbach conjecture
Says there are infinitely many primes, infinitely many twin primes. Okay, so if you wanted to do induction, what would you say? Suppose there are finitely many, you would try to get a contradiction. There's no obvious way to do induction at all in this case.
No, sorry, I wanted to say about this sum of.
Sorry, Goldbach's conjecture, not twin
yeah,
primes.
Goldbach
Okay,
conjecture.
Goldbach conjecture.
So suppose some even number is sum of 2 primes.
Yeah,
So next this n plus 2,
yeah.
whether that can be a sum of 2 primes.
You know these 2 primes. Now, how are you going to get the next 2 primes, even among the ones that we know? Okay. Now we take 4. 4 is 2 plus 2. 6 is 3 plus 3, or it's also 5 plus 1. You can write 6 as of course, 1 is not a prime, so let's leave that aside. It's 3 plus 3. And now let's take 8. So how do you write 8 as a sum of 5 plus 3? Okay. But there's no connection between writing 6 as 3 plus 3 and this one as 5 plus 3.
How to write that is different.
Yeah.
But whether it can be written as.
No, I
sum
mean,
of
how
2
would you
primes.
use induction? If you have done this, then you are going to use this to get the answer for the next one.
For n equal to 2, it is true. For n equal to n plus 2, if one can prove that.
No, there's no obvious way to do induction at all.
Okay.
I mean, unless, yeah.
I just wanted to make a comment. This point that you're making about in the field of mathematics, the greater pieces of work come from seeing connections between apparently disconnected parts.
Yeah.
This is actually true about physics also. The deepest works of physics seek connections between apparently dissimilar parts.
Correct, yeah. Thank you.
Last question in the formal part, and we'll end the session. So,
So would you say that it is convenient for the society that certain mathematical problems should not be solved? So for example, you gave this example that, nobody knows how one can factorize very large numbers into prime number, and all the crypto systems of banking are based on that. So discarding the possibility of quantum computers, so someday some mathematician, if comes up with a clever solution of this problem, then does it mean that all our online banking systems will become unsafe and we have to again start doing the banking?
No, you don't
that
have to
we were
start
30 years
again. I
ago?
think somebody who knows enough mathematics, and if they talk to computer scientists, they can come up with something which might take a few more years. But it's a permanent race.
Yeah.
So it's a question of who is smarter, whether the mathematician and computer scientist or whether the hackers.
So one last sociological question again. So you know that Hardy's famous statement that if a mathematician is older than 30, he or she is no good. So, so how do modern mathematicians view this statement of Hardy?
I think age is just a number.
that is the last question. Yeah.
Thank you for the talk, ma'am. I read somewhere that there is a connection between zeros of the Riemann zeta function and random matrix theory.
And?
Random matrix theory.
Yes.
And if so, can one think that the distribution of the prime numbers are random in some sense?
I'm not again qualified enough to speak on that. Yes, there is a connection. People have explored that, but just at a superficial level. But more interestingly, people have also tried to understand how to use random matrix methods to solve this other important conjecture, the Birch and Swinnerton and Dyer conjecture. And for a time, people were very hopeful, but they didn't get far in making dramatic progress towards the Birch, Swinnerton and Dyer conjecture using random matrix methods.
Okay, so I think, for the interest of time, so we'll end the formal part of this with inviting our director to present a small memento to Professor Ramdorai.
Thank you. Thank you.
So thank you very much for your attention. And so we can, of course, have informal questions after this, but we'll take a break from the formal part. Thanks a lot.